All right, so today we're doing a thing called the quotient rule, and we use that when we're dividing functions. Again, if you want the proof, you can look it up. It's in the text. Pages 397 and 398. Essentially, it is this. So if you have y, which is two functions u and v, you divide it by v, where u and v are functions in terms of x. Other thing is that v can't be equal to 0. It needs to be divided by 0 and you have undefined. So dy dx then is this. V times du dx minus u times dv dx over v squared. And that is the quotient rule. So it's a little bit more involved than the product rule.
Is it possible to, since u divided by v is the same as u times 1 to v, to just do v to the negative 1 and solve it that way?
Yes.
Or is that
No.
the same thing?
No, what you are saying is you could say that y equals u times v to the minus 1.
Yep.
And then you could use the product rule on that. Yes, you could. Okay. And sometimes some people will prefer to do that than use this, because this gets a bit messy. Sometimes this. But given it's on, it's mentioned in the study design, then that would need to cover it just in case there's something that specifically needs that. All right, let's have a look at some examples. All right.
So is that the simplified form, like equals uv to the negative 1?
That's something, that's if you were to solve it via the product rule.
You could, Alice asked if you could change this and write it like this, and then use the product rule, and the answer to that is yes. Oh. Let's just start with there we are. Alright, so first one, a couple of functions, sin x is one of them, x plus 1 is the other. X can't be minus 1. So u is the one on top, v is the one on bottom. And when we differentiate u, we get cos x, and v is x plus 1, and when we differentiate that, we get 1. All right. So this is our quotient rule. So dy dx. So we follow, we've got, so it says v times the derivative of u. So v times the derivative of u. So we've got x plus 1 times cos x. And from that we're subtracting u times the derivative of v, u times the derivative of v, so sin x times 1, and on the bottom is v squared. So we now got x plus 1, and we're squaring it. Alright, and that then just neatens up to x plus 1 cos x minus sin x on x plus 1 squared.
Can't you put it as cos x minus sin x over x plus 1?
Because you have to differentiate x plus 1 squared out of sin x and x plus 1 cos x. You could write it as probably cos x over x plus 1 minus sin x over x plus 1 squared.
You could, yeah. So just putting straight into these things straight in, that times that minus that times that, and then dividing it by this one squared, just putting it straight in, that's what you get. Yes, you could change that to other ways, but unless they indicate that you need to, you just leave it. Alright, so the next one. So our functions can be anything, and we just use the same things, the patterns that we know about the differentiation. So remember, the u is the one on the top, so e to the x. The v is the one on the bottom, so e to the 2x plus 1. We need to differentiate each of those. So it'll be e to the x and 2e to the 2x, yep. Right, so I'll just write the chain rule over there. Now this is on the formula sheet. The chain rule's on the formula, chain rule, product rule, not product rule. Quotient rule, get it right. Quotient rule is on the formula sheet. And you get a formula sheet in both exams, so you don't need to remember it. Alright, so it's v times du dx. So it's e to the 2x plus 1 times e to the x. From that we take u, which is e to the x, times 2e to the 2x all over e to the 2x plus 1 all squared. Alright, and then we would have a look and see whether there's anything that we can simplify, and there probably will be. So if I expand this out, e to the 2x times e to the x is e to the 3x, yep, because when we're multiplying we add the indexes. So 2x plus 1x is 3x, plus e to the x minus, when we expand that, multiply that into there, we get 2e to the 3x over e to the 2x plus 1 squared. So we've got an e to the 3x here, and we're taking 2 lots of e to the 3x. So how many lots of e to the 3x do we end up with? We've got 1, we take 2, we should have minus 1, shouldn't we? So e to the 3x minus 2e to the 3x. And so that's e to the 2x plus 1 squared. All right, one more example. Alright, so don't forget u is on 1 on the top, so u is equal to x minus 2, and the derivative of that is 1, yep. And so that means that v is the x squared plus 4x plus 1 bit, and dv dx is 2x plus 4. Yep. So then we follow the quotient rule. V times the derivative of u. So x squared plus 4x plus 1 times 1. From that we take u times x minus 2 times 2x plus 4 all over x squared plus 4x plus 1 squared. Then we need to, on the top, expand, collect like terms. So the first bit here is just x squared plus 4x plus 1. So it's just multiplied by 1. X minus 2 times 2x plus 4 is 2x squared, there's a minus 8, yes. There's also x terms.
But they cancel out.
But they cancel out, yeah, they do too. Yep, they do. 4x minus 4x, alright, yep. Square brackets, there's no significance other than it's a square bracket. Just, I wanted to make it different to that. Alright, so again, just to remind you, when it says take, it says take the product of this. So that's why I put the bracket there, to remind to take all of that. Alright, and so it's x squared plus 4x plus 1 squared. So, like terms, x squared here, take 2x squared, which will be minus x squared. 4x, there's none there, so it's 4x on the top. 1 minus negative 8 plus 9. There it is. All right. Any questions about that? Needs clarifying? No. So it's just a matter of assigning your U and V, differentiate each one, and then follow that. All right, that's 9K.